So today I am happy to introduce Andy Langford. He got his bachelor's degree from Georgia Tech in physics, and then he originally wanted to be an astronomer, but he got offered a part-time job working with Ravi Shankara and Doug Davis, and that kind of put him on a different path. So we went to grad school at UC Berkeley, got a PhD in chemistry, physical chemistry, where he studied formaldehyde and glycol photodissociation with C. Bradley Moore. After that, he came to Boulder to do a postdoc in GILA, and then after that, he became a research associate with the Aeronomy Lab at NOAA, and he's been there for the last 25 years. And in his spare times, he likes to spoil the dog and play in his band with his wife. And the band's name is Living Easy. So with that, I'll turn it over to Andy.
Thanks, John. Well, good to see a lot of familiar faces out here today. Even people who came all the way across town, you know, when they could have heard this at home. So thanks for making the trek. I'm going to talk about a couple of field studies that took place over the last couple of summers, small studies that you probably haven't heard of, CABOTS and FAST-LVOS, which were focused on the idea of how much does transported ozone influence surface air quality in the Southwestern U.S. This picture is from Great Basin National Park, which is on the Nevada-Utah border, and it often exceeds the current NACs during springtime, when it's just about as far from any urban location as you can get in the U.S. So before I go any further, all the data that I'm going to be showing you was brought to you by a whole bunch of other people, and not just me, including all my colleagues at CSD, both in the atmospheric remote sensing group and tropospheric chemistry group, and colleagues at GMD who launched ozone sondes during the FAST-LVOS study. The Ajax folks, Laura Arachi and company from NASA Ames, who flew during CABOTS and were planned to fly during FAST-LVOS, but unfortunately had mechanical issues. Scientific Aviation that participated in both field campaigns. Steve lost his Y. And Clark County Department of Air Quality, which also provided us with some of the data that you'll be showing. So I don't have to tell this crowd, but you need this slide. Why do we care about ozone? One, because it affects human health and welfare. The health primarily through the influence on the lungs and inflammation of the pathways in the lungs, which increase both health problems and mortality and asthma, et cetera, and also because it damages growing vegetation, including a lot of important food crops. And so as a result, the U.S. Clean Air Act first established the National Ambient Air Quality Standards, or NACs, for ozone, that recently it's been changed several times over the years, but most recently reduced from a value of 75 parts per billion set in 2008 to 70 parts per billion in 2015, and that's for the maximum daily 8-hour average concentration. So first, the good news. Over the last 20 years or so, there have been tighter NOx controls, particularly applied to power plants, et cetera, and ozone has generally been decreasing in the U.S., and the national average ozone design value, which is the 3-year average of the fourth highest maximum daily 8-hour average concentration, from 830 different monitoring sites, that average has decreased by about 10 ppb over the last 10 years. And that average value is actually lower than the current standard. Well, that's the good news, but the bad news is springtime ozone is still increasing across the rural West. This is some plots from Owen Cooper's paper that came out in 2012, looking at the trend from 1990 to 2010 of the 95th, 50th, and 5th percentiles of ozone measurements. And this is springtime, March, April, and May that we're looking at here. East Coast, rather dramatic decreases at the highest levels. But in the West, pretty much at all percentiles, it's trickling up a little bit. And if you look at the more updated versions of this, which go through 2015, you see something's pretty similar. You also see down at the 5% level that there are anomalously high concentrations often in the Southwest compared to the other parts of the country. And in fact, in many parts of the rural West, the ozone concentrations peak during the springtime, particularly in May and June, and not later on in the summer as you would expect if photochemical production, local photochemical production, is the primary source of this ozone. You'll also see from, this is 3 years of the mean MDA8 measured at the monitoring site at Jean, which is in Clark County, the southern tip of Nevada here, right near the California line, that there were frequent exceedances, even of the 75 parts per billion standard, and then even more exceedances of the 70 parts per billion standard over that period. So this is 300 kilometers northeast of Los Angeles and about 30 kilometers southwest of Las Vegas. So, and you see this sort of behavior at a lot of different sites with this peak during May and June. So where's this ozone coming from? Well, particularly since the local NOx emissions are decreasing, then you see more of an influence from what we call background ozone, which includes naturally formed ozone transported from the stratosphere or from lightning or from the photochemical reactions involving NOx and VOCs from the biosphere, and also production from fires, but also includes the effects of anthropogenic pollution, particularly in Asia, that's transported to the Western U.S. across the Pacific. So as these influences decrease, then proportionately those influences get larger. And particularly going to talk about this intercontinental transport and the transport from the stratosphere. And these two things are closely related. That I got this nice plot that came from ACOM here, so off the web page from Laura's group, the UTLS group. And basically, what frequently happens is pollution from industrial sources, et cetera, in Asia during the springtime can be sucked up into the warm conveyor belt of developing mid-latitude cyclones, carried across the Pacific by those cyclones, and then they frequently form tropopause folds when they reach the west coast of the U.S., and that pollution, which was carried up into the cyclone to the middle troposphere, can then be carried back down in these tropopause folds, or in the dry airstream of the cyclone. And this is something that happens pretty frequently, particularly in the springtime. Later on in the summer, a lot of that pollution gets lofted up into the upper troposphere by deep convection, so not as much as being transported across the Pacific in the middle and lower free troposphere. And also you have fewer of these cyclonic storm systems as summer comes on and the jet stream moves further north. So you don't have this mechanism really peaks in May and June, where you've got the combination of those two things occurring. So you get a lot of that transport. Stratospheric intrusions also tend to bring down more ozone. They're most frequent in the wintertime, but they bring down more ozone in the springtime because there's more ozone in the lower stratospheric reservoir that could be tapped and brought down to the surface. And as it turns out, the Southwestern U.S. is actually a global hotspot for these deep stratospheric intrusions. There have been several studies, including some from Peter Hess, that looking at this problem here, and by and large, they all find that this area has more deep stratospheric intrusions than any other part of the globe except for the Tibetan Plateau, which of course is higher and gets a head start on bringing that stuff down. So it's not exactly clear why more of these tropopause folds here. When the cyclones come across the Pacific, they may get another burst of cyclogenesis there, and which creates jet streaks, which cause the tropopause folds when they reach the west coast. But they do appear to be more frequent, and typically the intrusions will form up above the Pacific Northwest and slope down to the south, and with a maximum impact near the surface in Southern California and along Baja California. And if we look at some modeled surface impacts of transported ozone, so this is both the stratosphere to troposphere transport, or STT that I'll be calling it, and also the Asian pollution. This is from Mayan Lin's calculations she did for the CalNex period back in May and June of 2010, looking at the net transport to the surface from both of these mechanisms. And you notice a couple of things. One is the greatest impact by far is in the Intermountain West. And also that the distributions look very similar, and that again is because of that link with the transport by the cyclonic systems that is bringing a lot of the Asian pollution over to the Western U.S. But you'll also notice that the difference in concentrations, that the contribution from STT is about 4 times as much ozone as is coming from the Asian pollution transport. But they tend to be very tightly correlated and mingled, and often, these days at least, it's rare to see a stratospheric intrusion where there isn't associated Asian pollution that's being transported with it. And that the maximum here is in southern Nevada. There's really a hot spot right down there in southern Nevada. And after the CalNex campaign, and I gave a talk about that in Reno some years back, and there were a couple of folks there from the Clark County Department of Air Quality, and I was talking about stratospheric intrusions we had seen with an airborne LiDAR during that campaign above Southern California. And they said, hey, wait a minute, maybe this is why we're seeing these high values in the spring in Las Vegas, in the Las Vegas area. And would you be willing to bring your LiDAR out there and do these measurements? So we put together a small field campaign called LVOS, the Las Vegas Ozone Study, that took place back in 2013. And it was, you know, a fairly small, low-budget campaign. It consisted of our truck-mounted now ozone LiDAR system, Topaz, same system that had been on the plane that Ivan flew with in 2010, but we now put it in a truck and it looks up instead of looking down. And it has a scanner on top so we can look at different angles from horizontal to vertical and measure a profile that extends all the way down to within about 20 meters of the truck or so. We also brought out some in situ measurements of ozone and CO, and we took these out to this place called Angel Peak, which is about 45 kilometers west of Las Vegas at about 2.7 kilometers above sea level. So roughly the same as Fritz Peak, which is a place I used to work up at near Rollinsville, same elevation. And we had these measurements up there for a period about 6 weeks, and we saw quite a few layers of high ozone and with or without associated aerosol that appeared over Angel Peak during that time. This is just showing the measurements from 1 week, and these time height curtain plots, each of these is anywhere from 4 to 20 hours or so long of the ozone concentration from the surface of Angel Peak up to about 5 kilometers above sea level. And then each of these horizontal stripes here are surface measurements made either at Angel Peak. This was actually made at Echo Peak, which was part of the North Las Vegas Rural Ozone Initiative, May Gustin's project. And then several other measurements from monitors in Clark County. And the lowest one is actually from Death Valley, which is on the other side of Mount Charleston here, which is the highest peak in the Spring Mountains. And what we found is that after many of these intrusions and large layers here, we saw high ozone the following day down in the valley, including all the way down into Death Valley. There were exceedances of the current standard in Death Valley, and that monitor is 200 meters above sea level. It's not just the higher elevation peaks. What I've plotted over here, then, that's a correlation between ozone and CO that we measured at various times during the study. And when you're looking at sources, since most ozone is coming from ozone is higher in the upper troposphere and lower stratosphere, but CO is higher near the surface. When you're getting transport of air from the surface, they tend to be positively correlated if that ozone's coming from the surface. And we've got some different regimes here, from Asian pollution to a biomass burning, and then even marine boundary layer air that we saw up there on top of Angel Peak. And then some of the UTLS air where there's a negative correlation, that there's higher, as ozone goes up, CO goes down. And that's a signature along with the dryness of UTLS air descending to the surface. So we actually saw that come down to the surface of Angel Peak. So we inferred from those measurements, even though we didn't have anything other than these surface measurements down in the valley, which is 700 meters above sea level, that this ozone was making its way down there. And the likely candidate seemed to be just entrainment by the mixed layer. I plotted here in black the mixed layer depth from the McCarran Airport radiosondes. And you can see those often got up to 4,500 meters above sea level or so. So high enough to entrain some of this ozone that's being transported between 4 and 5 kilometers above sea level. So that was our hypothesis, but we didn't have direct measurements of that process. So after we published some of the results from LVOS, we were approached by CARB, the California Air Resources Board, and the San Joaquin Valley is one of the two extreme non-attainment areas remaining in the country, the other being the South Coast Air Base in the LA area. Those have the two highest ozone of any place in the US right now. And so CARB and the San Joaquin Valley Air Pollution Control District people were wondering, maybe some of this transported ozone coming from the stratosphere from Asia is causing some of the high values we're measuring in the San Joaquin Valley. So they funded a small project called CABOTS, which took place in the summer of 2016 in June and July. And this was a little bit bigger than the first LVOS campaign. So in addition to the Topaz ozone LiDAR, which we parked out here in Visalia in the central San Joaquin Valley, they also were funding some measurements from UCD and Scientific Aviation to fly the Mooney, Steve Connolly's, one of his instrumented aircraft, which are parked right over here at the airport, throughout the valley and try to understand the distribution of ozone from that. They funded measurements at Chews Ridge here from Ian Faluna's group at UC Davis. And then daily ozone sondes were launched during the whole period by San Jose State University, mostly at Bodega Bay, but also down at Half Moon Bay for part of it. And the Alpha Jet from NASA Ames made at least 3 flights during this time that we were able to compare to. And at the very end of the campaign, we shipped out a brand new micro-Doppler LiDAR system that was developed in our group at CSD. And that system was just a vertically pointing Doppler LiDAR. So it measured the vertical velocity variance, which is a direct measure. We can get a direct measure of the mixed layer height from that. We only had it out there for the last couple of weeks, but those measurements proved very, very interesting. Now, just a little bit more about the LiDAR. It's tunable UV ozone dial based on a cerium LiCAF solid state laser. And we measure both ozone and aerosol backscatter profiles. And the way we do that, again, is by cycling through and measuring profiles at at several different angles here, and by splicing together the vertical components of these profiles, we can fill in this region down here. All LiDAR systems have a blind spot, basically near the transmitter, so you can't see what's closest to you. And this was our way of getting around that and being able to measure all the way down to the surface, again with the caveat that over the integration time that we're looking at, that things are horizontally well mixed. And sometimes that isn't always true. And so you have to take that into account. So that's how you create a profile all the way down to about 20 kilometers. And it's also important, the system is automated, but it's not autonomous. It takes a couple of people sitting in that truck to keep the thing going. So all those hours of measurements involved human bodies. Unfortunately, the weak link here is this laser, which there's no suitable replacement for it, and it tends to burn itself up and requires attention every couple of hours. You can't fully automate the system because of that. But anyway, we were there for 2 intensive operating periods, IOPs, and we measured a total of 435 hours of LiDAR measurements over that period, split roughly into those 2 times. And very, very complicated. Just many, many, many layers above the valley, and all kinds of dynamics going on there. You know, it's interesting to compare these to the winds that we have from. We're located right next to a radar wind profiler, and very much of the structure that you see in there is caused by differential advection, and particularly when you see things, it looks. You might look at a time-high curtain plot and it looks like something's going down. Well, you look at the winds and nothing was going down. Things were actually sliding over each other. So it's going to take a while to really understand everything that was going on there. But we did see, and we also measured aerosol at the same time, and we did see, though, some clear periods where these layers that were coming down were primarily due to some stratospheric intrusions, major intrusion right here, and then transport layers from Asia. And so I'm going to focus over this period right here. Major local production episode where there's contributions from the Bay Area, from within the valley, and even from the South Coast Air Basin getting up into there. And then the second IOP was really dominated by the Soberani's fire, which I'm not really going to talk about. So I'm going to focus on this region here, and just gives you, at the beginning of that, the synoptic overview, where these are the geopotential heights at 300 hectopascals, and you see this moderately deep trough situated over the Western U.S. And there's also a jet streak, you know, a localized wind maximum that appears down off of above Southern California. And typically the jet streaks is where the tropopause fold forms. And that's pretty much a classic situation. We saw this sort of thing a number of times during CalNex, that you would get these intrusions, and at other times as well. It's very common during this time. Some model results. These are from the NOAA GSD RAPChem, so these are WRF-Chem results, George Grell's group. And that shows for the same time, or this is 12 hours later, you can see this intrusion here on the 500 hectopascal surface, which is about 5.8 kilometers above sea level. There's the tip of the tropopause fold, and there's a filament. There are filaments here that are going across the San Joaquin Valley. Also, if you look at the total CO, you could see that there's CO pretty much following that same pattern there, and that's pollution which has been transported by the cyclone and then mingled with the stratospheric air as it descends. This is broken up a little bit more with these FLEXPART tracer analyses. So now, whereas the WRF-Chem results were showing you total ozone and total CO, this is actually splitting things up into a stratospheric tracer component that starting in the lower stratosphere, and then an Asian pollution component for CO, which is starting at the surface in Asia. And again, a similar pattern, but a lot more of this ozone here. You see this filament, these filaments going across the west coast here and across California of that high ozone from the stratosphere. Mostly the Asian pollution, it's a little bit hard to see where this is chopped off, is trailing along kind of behind the stratospheric component. You can't really measure these compare these directly because this being a tracer of CO emissions, you can't convert that directly to ozone, although probably it's based on plume studies, it's probably on the order of 3 to 5. The amount of ozone in that plume is 3 to 5 times smaller than the CO. So quite a bit smaller than the ozone from the stratosphere. We can compare that to the measurements now. This is 8 days from the LiDAR showing the tropopause fold here, and then these high ozone layers here. Here again is the time height plot of the stratospheric ozone tracer that right above Visalia where we were, and you can see excellent job of really picking up this intrusion here. I mean, really quite remarkably well. And then over here is the CO, the Asian pollution tracer from the same time. And you can see it's staggered a little bit after and behind stratospheric intrusion and a little bit lower there. It doesn't quite, you can see during this period here, there's no stratospheric tracer, but there is Asian pollution, although the peak appears a little bit earlier and a little bit lower than what we're actually seeing in the measurements. So they're a little bit different, but still not bad. So I'm going to look at these 2 periods here, the measurements on the 12th, where we're pretty much dominated by the stratospheric intrusion, and then the 15th, where we're really just looking at some of the Asian transport. This is the same thing, but now expanded a little bit for the 12th. Again, really quite close agreement there. And then if we look at the 15th there. Now on the 15th, we also had a flight from Ajax, so we're able to compare the sexy fighter jet to our 1987 truck. And this again is the time height curtain plot of the ozone measurements, and superimposed on that you might see a dotted line which represents the flight track of Ajax. And this area right there where it's more than a dotted line, it actually has the blocks. That's when it was within 5 kilometers of Topaz. So basically they came and they did a spiral descent around the LiDAR. And these are the measurements expanded to show that time. And you'll notice a couple of things. One is very good agreement between the LiDAR and Ajax. And 2, they just barely, ever so slightly got up into the high ozone layer there at about 5.5 kilometers. They're just starting to see it here when they hit their ceiling. And that's, the jet can fly a lot higher, but their 2B ozone monitor can't operate higher than that. They run into some pressure problems. But whereas the LiDAR can sit there and measure for many hours, the jet can fly around and do the spatial sampling that we're not able to do. And they actually flew from NASA Ames here, and then they flew by way of, in Sequoia National Park here, there was a little control burn called the Goliath Fire that was taking place. They flew over that. Then they flew to us at Visalia and did their spiral profile. So here they are, do their profile, and then they fly north to Bodega Bay and do a profile near an ozone sun launch, back up and down. So this is the flight path then corresponding to that track. And they picked up that Asian plume up here and did confirm that this higher ozone that they're just barely in it's upper tropospheric. You see how dry it is, but it also has enhanced methane or enhanced CO and a little bit of enhanced methane with it. But compared to the fire plume down here, where there's maybe a tiny bit of ozone enhancement, a lot more CO2, and a lot more methane associated that, but a lot moisture. The fire plumes have a lot of water in them as well. And that's one way to distinguish them from the pollution plumes, which have descended from the middle and upper troposphere and tend to be quite dry. So we have several other flights here. So this is just some nice results. Now, the model here shows ozone reaching the surface during this period after this finger descends right down there. And, well, we're only human, and we measured for 24 straight hours there, and then we had to sleep. So we weren't able to measure during this period. That's why there's a gap in the data. And so the question is, did it get to the surface? So we have to rely on surface measurements for that. This is looking over the whole week right there. And I'm showing down here some surface measurements from 3 high elevation sites from the White Mountain Research Center, Joel Burley's organization. And these are quite high. I think the highest summit there is about 4,050 meters where they've got a monitor that they try to keep going. They can't get to it in the winter. And sometimes it gets snowed in, and occasionally it gets incapacitated in the wintertime, and they lose some data. These other sites they can reach during the winter, so at about 3,900 and about 3,200. But all of these sites during this period here where we were sleeping, during that early morning part, they saw an increase in ozone. And the highest elevation site here, which you see intersects that filament coming down directly, saw ozone up to about 75 ppb for even for the 8-hour maximum daily 8-hour average. And then the lower sites saw progressively less ozone. They also saw high ozone, the same thing, on the 16th as well. And then this was followed by some lower ozone air. So it clearly directly intersected the surface at these high elevation sites and while we were still measuring. What about lower down? Well, as we work our way down, there are a couple of sites in Lower Kauai and Kings Canyon in Sequoia National Park, almost 2 kilometers there. And those are the measurements that are shown here in the dotted and dashed lines. And did they see any enhancement? No, ozone actually went down after the intrusion. And if you look at a site in Porterville, which tends to be one of the most polluted sites in the San Joaquin Valley, it also went down after the intrusion. In fact, if you were to throw in some sites now from Southern California, I put in Crestline, which, if you're familiar with that, that's up near Lake Arrowhead, elevated site that tends to measure the highest ozone concentrations in the South Coast Air Basin and hence the entire country, because they get the transport up from LA, upslope transport, and they sit in this muck for pretty much all the day when the sea breeze comes in and clears things out down below. Well, they're typically measuring 110 to 120 ppb of ozone every day, except after the stratospheric intrusion when ozone drops down to manageable levels. So what a lot of people have the idea that stratospheric intrusions bring a bucket of ozone down and add it to the bathtub that's at the surface, but that's not what usually happens at all. That in the frontal, the descending air behind the front here displaces all the air down near the surface. So you've taken air which was highly polluted with 80, 90, 100 ppb or more of ozone and replaced it with air which has 60 to 80 ppb of diluted stratospheric UTLS air, which, you know, as the stratospheric intrusion descends, it entrains tropospheric air, and so the peak concentrations decrease the lower they get. We saw the same thing in CalNex, you know. Ironically, in the place which gets the most stratospheric intrusions impacting the surface, the net effect is to clean things up, because what was there before the intrusion was much more polluted and had a lot more ozone in it. Meanwhile, back in Las Vegas, after we saw that, well, ozone went up in Las Vegas, and it went up from 40, 50 ppb or so up to nearly 70 ppb on the day after that intrusion took place. So we still had some unanswered questions from Elvis, you know, and particularly, how does that transported ozone reach the valley floor? And indeed, is that really what's happening? Is that really what we're seeing? So Clark County asked us to come back, and so we cooked up a plan for FAST-LVOS, which Fires, Asian, Stratospheric Transport Las Vegas Ozone Study. So we brought in more things, more measurements to try to get a better understanding of what's going on in the valley. And, you know, I really wanted to call this FAT-LVOS, but I felt I just couldn't leave out the stratospheric part. So it became FAST-LVOS instead of FAT-LVOS. And we learned a lot about fires, but I'm not going to talk about that. We've got a lot of interesting data from fires. So anyway, FAST-LVOS. You may or may not have noticed when I showed you those curtain plots from Angel Peak compared to the ones from California. The ones from California went from near sea level up to 6 to 8 kilometers, and the ones on Angel Peak only went up 2 or 3 kilometers. Well, we made some improvements in our system between those two campaigns. So we brought that improved LiDAR system back out to Las Vegas, but now we parked it down in the valley at the North Las Vegas Airport, which is 700 meters above sea level, instead of 2,700 meters above sea level. Incidentally, it's about 20 degrees warmer, too, than Angel Peak, which is kind of a pleasant place to be in the summertime. So now we were able to measure up to 6 to 8 kilometers above sea level while sitting down in the valley. We also brought that Doppler LiDAR system back now, and we had it for the entire campaign to measure the mixing heights and test this hypothesis, whether we were entraining that ozone by just mixing. On Angel Peak, we brought a mobile van from mobile lab from the Trop Chem group, which instead of just ozone and CO, now we had a much larger complement of measurements, including NOx, N2O, and methane, and water. So we parked that up on Angel Peak for the most of the time, but it made a few forays down into the valley. And then our friends at Scientific Aviation came, and we had about 90 flight hours with them, where they were based at the North Las Vegas Airport and did profiles over the airport, over Angel Peak, over Jean, which I talked about earlier, all the way down to Big Bear, did a profile over Barstow, and then flew back. So we had a lot of information from that. And we also had ozone sondes from GMD. Now, we didn't have the funding to have the aircraft and the ozone sondes continuously for the 6-week campaign. So what we did is we looked for propitious synoptic conditions that would enable us to say, okay, there's likely to be transport in the next few days. And then these guys would fly out and launch ozone sondes or fly the aircraft over a 3 or 4 day period. So we had 4 of those IOPs during the campaign. A lot of that summarized here. They flew on 14 days. Topaz measured 45 consecutive days here. Again, a lot of elevated ozone. Measurements on Angel Peak, 41 days there and 6 driving around. Again, flights down to Big Bear and back. We had a 6-hour flight plan. Ozone sondes, we measured up to 270 ppb of above 6 kilometers with both the LiDAR and the ozone sondes during a major intrusion event that took place in the second week of June. And then here are the Doppler LiDAR measurements of the mixed layer heights. You can see that scale goes up to 5 kilometers above ground level. And it just barely gets the highest measurements that the mixed layers are extremely deep. And you think about it, in the Mojave Desert, there's no water that's going to be evaporated, and there's very little absorbing, vegetation absorbing the solar energy. So pretty much all of that energy can go into sensible heat and drive these really deep mixed layers up to over 5 kilometers deep. So a couple of examples. Here is measurement during that stratospheric intrusion I was talking about, 270 ppb right here. Here's the time height measurements from the ozone LiDAR for that 12-hour or so period. This is part of a panel of 60 hours of continuous measurements. We had 2 teams, and we traded off every 12 hours and measured for 60 hours straight. And it's pretty impressive. This is the mixed layer height from the Doppler LiDAR. And this is particularly interesting because that mixing is driven, it's turbulent mixing driven by winds. It's not convective mixing during that period. And we had these high winds here, which grounded the aircraft after a short flight around the area. There's just the flight path showing colorized by the ozone that they were measuring. But they basically had to land and couldn't fly. But Patrick Cullis heroically still managed to get off 4 ozone sondes during that time. And those correspond to these stripes right here, which are superimposed on top. And if you can't see them, I mean, the less you can see them, the better. That means, you know, the measurements are agreeing, so they're blending right in. There were some places where you could see that there was spatial differences. You know, the measurements agree quite well most of the time, so that when they don't agree, we're pretty sure that's horizontal inhomogeneity. The ozone sonde was launched about 8 kilometers from where the LiDAR was, and then it went downwind from there. Measurements at Angel Peak, you can see periods when ozone goes up, both N2O and CO go down. And Angel Peak is sitting at about this elevation, although obviously shifted 45 kilometers away. But during this period here, when we've got this wind-driven mixing, the measurements, ozone measurements measured at Angel Peak are very close to what's measured down in the valley, that we're really mixing things down. And so we've got that direct mixing and entrainment down to the surface that we had to infer before. But again, in this case, it only got up to about 60 to 65 ppb, not enough to cause an exceedance like we saw several times during the first LVOS campaign. 3 times stratospheric intrusions directly caused exceedances during the first campaign. This campaign, 0. There was a couple of indirect exceedances caused by stratospheric intrusions when the stable air comes down and caps the mixed layer, and so the local production builds up and you get localized exceedances. So we saw a couple of examples of that, which I'm not going to show you the data, but in that case, the mixed layer height, because of that stable layer, was only 1 to 2 kilometers. One other example I'll show you is entrainment of an Asian pollution plume. So this is kind of the smoking gun. This is what we went to see, and there it was, and we saw this on quite a few different days. Here's the mixed layer height from the Doppler LiDAR, convective mixing. Here's a plume with high ozone picked up by ozone sonde and also by scientific aviation. They flew profile in the morning and in the afternoon. You can see the difference over here. The morning has high ozone and high methane, as a pollution plume, and not stratospheric source for this here. And in the afternoon, both were mixed out and gone. But there was no aerosol to speak of with this plume, so you know it's not related to biomass burning, for example. And the back trajectories here, we don't have model results yet, that in this narrow layer the back trajectories do go back to Asia. So, very interesting. Now, if we contrast these two things, you know, it does reinforce this hypothesis we had about the role of these deep mix layers. And so I've plotted here as it happens, Visalia and Las Vegas, Angel Peak, Choose Ridge, they're all at basically the same latitude. So you can just draw a latitude stripe across there. Here's the topography in orange here. And Visalia sitting here. These are the mixed layer heights that we measured with the microdoppler LiDAR in Visalia. Here are the mixed layer heights we measured with the microdoppler LiDAR in Las Vegas. 105 degrees at both places. The mixed layer is 5 kilometers deep in Las Vegas. It's 800 meters deep in the Central Valley. And the reason for that, there's several things contributing to that. I told you why those are so deep, all the sensible heat and no latent heat. But the opposite is true here. There's a lot of irrigation taking place. A lot of that energy goes into evaporating water. There's large-scale subsidence associated with the persistent Pacific high, which is sitting off the coast. And there's subsidence associated with the return flows from the orographic flows in both directions. All those things are pushing the mixed layer down. And in the summertime, it rarely gets above a kilometer deep. So you're not seeing the entrainment of these elevated layers like we saw in Las Vegas. It's just not happening in San Joaquin Valley. And so these layers can move across. They can cross the Sierra, cross California, and then get entrained further inland. And that's the main reason for the hotspot in the Intermountain West for transported ozone and stratospheric. So finally, those are the conclusions, which I basically have just said. Thank all the supporting organizations here, and thank you for your attention.
Any questions?
None.
I have two, but
Okay.
So the AJAX flights, what all were they measuring?
They had methane, CO2, water, and ozone. They didn't have formaldehyde on those flights. They, I'm trying to remember if they had formaldehyde on any of those flights. They might have had it on some of their flights, yeah. But that's what they have. Both aircraft have a 2B monitor, which have been heavily modified.
So what are your future plans to go on this research? Are you going to continue to try to find it out even better, or?
I'm looking forward to a summer with no field campaign to actually have a chance to look at this data. You know, we've barely begun to scratch the surface. The CABOTS data, you know, we almost immediately turned around and took another data set. You know how it goes. And so you rarely get to look at more than 10% of the data from one field campaign before you're on to the next. So I'm looking forward over the next year at least to be able to really dig into this. Yeah.
Hi, Andy. From the topaz, you also get aerosols?
Yes.
And is there anything, like, are they collocated with those intrusions with ozone? Or
well,
something
the
like
intrusions tend to have low aerosol. There's not a lot of aerosol in the lower stratosphere right now. It's funny, back when I first started looking at stratospheric intrusions, way back in the 90s, that one of the signatures of a stratospheric intrusion was high ozone and high aerosol, because you were entraining aerosol from Pinatubo, you know, which had filled the stratospheric reservoir. So a finger of high aerosol accompanied that finger of ozone. Now it's just the opposite, that the stratospheric air tends to have less aerosol, And the transported pollution can go either way. It depends on the history of the air mass and whether there's been any rain out, et cetera. And very often there's no aerosol, but sometimes there is. So you can't use it as a definitive tracer either way for Asia.
Could you say a little bit more about those stratospheric intrusions? What are the mechanisms? What's the time scales, and what are the horizontal scales of those intrusions?
I've chopped off this. See if I can skip back faster than going back through. A couple of these are really slow slides. They're fairly large. I don't know if you saw. If you go back to this plot right here, very often they tend to often form on the western flank of these troughs. So, but not always on the western flank. Basically, whenever there's a jet streak, you know, the jet stream is not following geopotential surfaces. So when you see these enhancements, you often get a tropopause fold form. And so they cover many hundreds of kilometers. They're often quite large, but at the same time, if you go back and look at the measurements from CABOTS that I showed, that's kind of the classical, if you will, kind of a classical intrusion where you see this tongue of descending air seen in cross section. And that's, you know, the jet stream is over here, and this tongue is coming down below it. And but this one has some interesting stuff. This may well be Asian pollution here. Exactly what's going on here isn't clear, but it may be related to mixing, or it may be horizontal. So that's kind of the classical view. But if you look at something that's not in that cross section, and the measurements from both of the LVOS campaigns typically showed very complicated structure. And we saw this thing over 60 hours, basically. It took that long for the whole thing to pass over our site there. Ironically, the thing was so far to the south that there really wasn't much influence on Las Vegas. But looking at the surface measurements, it looks like there were probably surface impacts in Arizona and northern Mexico. That's where more of it got down to the surface. And also that when you had the strongest mixing going on here, and there's some mixing at night as well, because driven by the winds, it didn't correspond to when you had the highest ozone available. So just by luck, you didn't get as much to the ground this time for such a huge intrusion, but they can be quite large.
So a lot of people say that background ozone in the West is increased because of increased pollution coming from Asia. So wouldn't you expect that trend to reverse over the next 10 or 15 years?
Some people think it already has, or at least that it's peaked or plateaued. I'm not sure that's obvious, but there are people who are suggesting that it has done that already in the last couple of years. So I'll be able to tell you for sure in another 10 years. Yeah. So.
And I know you didn't want to talk about it, but do you always see ozone increases with the wildfire influences, or is it all over the map?
We have, by and large, but again, we've always been fortunate to be a couple of 100 kilometers, 150 kilometers from the closest fire, and in that case, we did see production. That Goliath fire, it was a small fire and a controlled fire, and it was only 20 kilometers away. We didn't see any real production. We were too close, I think. You see titration when you're really close, and the ozone goes down, and then you get a certain amount of production. as you know, and then you run out of NOx, and you stop seeing production until maybe 1,000 kilometers later when the pan decomposes. So it's Sobrani's fire, which is about 150 kilometers west at Big Sur. We saw a lot of production, a lot of ozone, well over 100, 120 ppb of ozone in some of those plumes coming from that fire. Yeah. And we saw also some production in Las Vegas during FAST-LVOS. We managed to get the F, the A, and the S.
That was kind of my question, but I did have one more, and that is on one of the first slides where you were talking about the TTL influence on ozone. I think the color scale showed up to maybe 20 or 30, maybe 40 ppb enhancement. Is that at the surface?
Yes, that's at the surface.
So
those are the AM3 model results.
Yeah. So in the absence of that, is that saying that that area would then have an afternoon average of more like 40 to 50 ppb rather than 70 to 75? Well, or am I reading too much into that?
Well, you have individual intrusions, which we're looking at here, but at the same time there are many intrusions that get averaged hemispherically and over a large area. So the background in springtime in the free troposphere tends to be higher. In general, it tends to be 50 to 60 ppb. And then an individual intrusion might bring more and even push you up over the 70 ppb limit, plus fires, plus, right?
When I saw this, I thought I'd forgotten about it by the end of the talk. When I saw this, I was thinking, well, if the trends that were observed in the Western U.S. were indeed brought about by Asian pollution trends, they would be almost impossible to detect if it was really 4-1, right?
Why? Well, there's a lot of interannual variability in the stratospheric contribution. Whether or not there are any long-term changes is, some models say yes, some models say no, in terms of intrusions. So, yeah, it's hard to say what trends are. I don't deny that. Yeah. Now, theoretically, you might think that the stratospheric contribution is more constant and not just ramping up. I mean, constant in this sense, where large year-to-year differences and related to El Nino and La Nina, et cetera. But those same, again, that's driving the transport, which is going to influence the Asian transport component as well. And you see that interannual variability there as well. So trends is a tough business.
So was this CalNext campaign just coincidentally the same time of year, or was this part of it too? I thought it was separate, but
I think it was more coincidentally, really. Yeah, Michael was nodding that it just happened to be in May before hurricane season, because that's when the P3 is available.
Because then the P3 is unavailable?
Yeah.
Okay.
Yeah. The Twin Otter actually flew in July as well, so we had measurements after the P3 left.
I could just mention that the Moppet satellite data also show episodic transports of CO across the Pacific, and which maximize in the spring.
Uh-huh.
Okay, if there's no more questions, let's just thank our speaker again.
Thank you.